All right, everyone, I think we will officially get started with the presentation. So thank you all again for joining us for the August session of Virtual Lab Notes. This is now our fourth session that we've done, and we're very excited to continue this series. Just as a few reminders, make sure that you keep your microphone muted through the entire presentation, and also that your video is turned off. That will help us save bandwidth with Wi-Fi and everything. Also, please use the chat function on the panel if you have any questions. You can ask throughout the presentation, but I will ask the questions to Dr. Steffen at the end of his presentation. And if you have any issues during the meetup, make sure that you check out this link, support.google.com/meet. They should be able to answer any questions that you have. And then we are recording the presentation. If you can't see that up in the corner, this is being recorded. And it will be available for viewing within the next week at unlv.edu/sciences/virtual-lab-notes. It's quite a mouthful. But before we get started, just wanted to let you know that we do have a September lecture coming up. So the next session of Virtual Lab Notes will be presented by Dr. Audie Picard in the School of Life Sciences. We're excited to have her join us, and her topic will be influence of microorganisms on mineral formation, how microbe-mineral interactions can help us look for life on other planets. Should be fascinating, and we're very excited to have her speak to us next month. That'll be on September 30th at noon Pacific time. And look for emails with that information coming out as well. Should come out within the next week or so. And with that, I'd like to introduce our speaker for this month, Dr. Jason Steffen. Dr. Steffen is an assistant professor in the Department of Physics and Astronomy at UNLV. His work spans a broad range of topics, including experimental research into gravitation, dark matter and dark energy, the search for extrasolar planets, and the fastest way to board passengers onto airplanes. It's a very interesting article. You should Google it if you've never read it. Recognizing the importance of technology for improving the human condition and the energy needed to develop and supply that technology, Dr. Steffen teaches a yearly course entitled Physics for Future Presidents, where students walk through the science that drives modern society. So without further ado, I'm pleased to introduce Dr. Jason Steffen to present to us Gods of Power, How Nuclear Energy Will Save the Planet. Take it away.
All right, thank you. Hopefully everyone can hear me okay. So let me bring up the presentation. All right, so Gods of Power, that's the title of the talk I'll be giving, specifically speaking about Uranus, Pluto, and Thor, which are the three main nuclear fuels that are used in reactors. Although you could potentially build something also out of americium, but there isn't any Greek god named after America. I'm going to start off with a small history lesson from about a decade ago. This image shows the aftermath of the earthquake that took place in Haiti in, I think it was 2010. They had about 100,000 people died in this disaster, and a lot of that was caused by the collapse of the buildings. So they had relatively poor infrastructure. The buildings weren't reinforced, and so they basically crumbled and trapped people underneath. The road conditions, electricity, hospitals, lack of supplies, and the ability to get those supplies delivered took the death toll up to 100,000 people. That's a huge amount for this earthquake. So if we wanted to rebuild Haitian society, there are a number of things that you'd want to do. First of all, when you build a building, you want to use steel reinforced concrete rather than just straight up concrete, because the steel reinforcement makes it much stronger against tension that's put on the building during the shaking. And so you want to have steel reinforced concrete, you want to have better roads, you want to have deliver food so that everyone is adequately fed. Haiti is the poorest country in the Western Hemisphere. And at the same time, this is motivated by concern for the people who live there, which is the same motivation that drives a lot of the discussion about climate change, is concern for how it's going to affect people, not only in the United States, but around the world. But these two aspirations come into conflict when you consider the fact that cement production here. So this is what is necessary to make concrete. It's necessary to make a whole bunch of things. So you want to be able to produce the cement. You need to be able to produce the cement that you want to make the buildings. You need to have the steel put together so that you can make the steel reinforced buildings and improve the road beds and things like that. You also need to have fertilizer. If you want to feed the world, you have to use fertilizer. This is how you feed 8 billion people. You also want to be able to transport those goods from one place to another, which requires oil refining, both for the transportation itself, like for working in the cars and the trucks and the boats, but also for making asphalt. All of these things combined these are the major industries that emit the carbon dioxide. So this is a flow chart looking at the sources of greenhouse gas emissions across all sectors of the economy. This is for the whole world. The United States is a little bit different than this, but not significantly different. And I'm going to zoom in on a portion of this graph. It's pretty complicated, and there will be other ones similar to this. They're a bit less complicated. But if you look at this plot, so this shows where the energy comes from, like what form the energy comes from, and then the greenhouse gas that's emitted on the other side. So let me back up a slide. So this is carbon dioxide right here. And so that's the bulk of the greenhouse gas that is emitted. Some of this is methane, but that mostly comes from the agricultural sector. So if I zoom in, you'll notice residential buildings. So that's all the heating and air conditioning and light bulbs and stuff for residential buildings. This is worldwide. In the United States, it's a slightly smaller fraction of the economy. But about 10% of greenhouse gases comes from residential buildings. If you look at cement production and iron and steel production, those two together are equal to the amount of greenhouse gas emissions just that comes from residential buildings. So there's a huge amount of the stuff that comes from these heavy industries: iron and steel, cement production, chemicals, which would be like fertilizer, aluminum, paper production. Paper production is 10% of the greenhouse gases that come from, what's the best way to put it? Of all the greenhouse gases that are produced because of residential living, 10% of that, the equivalent of 10% of that, is just to make paper and other paper products like cardboard. And then you have oil and gas refining. This is not the use of oil and gas, but the refining process itself is another thing. Together, that they total twice the use or the production of greenhouse gases than all of the people living in their homes. So these are big industries, and there's a reason why these industries create or emit these greenhouse gases, and that's because they take place at high temperatures. If you want to make cement, you have to raise the temperature of the different ingredients in that cement up to about 1500 degrees Celsius in order to get the right chemical processes to happen. You have to dissociate certain things and reassemble it in other ways, and the only way to do that is at high temperature. So they have a gigantic natural gas flame that shoots up inside this kiln to raise the temperature up high enough to get the cement convert the limestone and the other ingredients into the cement that's eventually going to go into the concrete and the grout and stuff like that. A similar thing happens with the production of steel. It has to take place at high temperature. The production of fertilizer also takes place at high temperature, where you take natural gas and you mix it with nitrogen and with water, and you heat it up hot enough to rearrange the chemical bonds in that mixture so that you get your ammonium nitrate and produce carbon dioxide and water out of that. So that's where this stuff comes from. Our society depends upon these building materials. If it was easy to build something like houses out of something besides cement, or roadways or driveways out of something besides cement, we would do it. One of the issues that we face is that the cement is an exceptionally good building material. And so if we want to have buildings that don't fall on our heads, then we need to build them out of these kinds of materials. And especially in developing nations, because cement is relatively cheap, that's the kind of stuff that you need to build houses and stuff out of in developing nations. They don't have the money to make carbon fiber automobiles and stuff like that, or carbon fiber a lot of things. Some of the solutions that are often proposed for the general society about how to combat climate change, in many ways, are just band-aids on the real issues, because the real issues are these industrial applications and the transportation applications, and not so much the electric grid or how we use electricity in our homes. Not that that doesn't make a difference when you have 300,000 or 300 million people using electricity, but the elephants in the room are industry and transportation, not so much residential electricity. So, people will often tout, to buy an electric vehicle because electric vehicles have no carbon emission, which is false to begin with. They don't have emissions once it's purchased, but the construction of the vehicles does have carbon emission, and it has as much as, or even more than a standard car to make an electric vehicle. But that being aside, this is, if we all were to switch to electric vehicles tomorrow, it would cause a significant strain on what our infrastructure looks like today. This is another flow chart. This is put out every year by the Department of Energy. Let me expand the view here so that we can, well, it's not going to be easy to see all the details, but there are a few things that are important for me to point out. Again, we have the sources of energy on this side. So there's solar and hydro and natural gas, petroleum down here. And then they all flow into a bunch of different applications. These are the applications. So residential energy use is right here. Commercial energy use is right here. Industrial energy use is right there. And transportation use is right here. This is for the United States. Again, you can get this at Lawrence Livermore National Laboratory. They have similar breakdowns for every state in the union and also different countries around the world where they've done a similar assessment. The important thing to note here is that transportation is twice as big in terms of energy demands as residential electricity. And so if we were, and the amount of energy that goes through the electric grid is this orange block. So a number of things, coal, natural gas, hydro, geothermal, stuff like that, all go into producing electricity. And then some of that energy is wasted simply because nothing is 100% efficient. Efficiencies, if you can get efficiency of 50%, you're doing pretty well. With electricity production, the efficiency is about 30%, and so, or about a third. And so the amount that we can use from electricity generation is the orange, and the amount that we cannot use simply because it's an inefficient process, as is everything, is the gray. So the gray is energy that's lost through inefficiency, and the orange and that we get here is the energy that we actually get to use in for our different applications. But the amount of electricity that actually goes into transportation is a tiny, tiny fraction of what the demand would be. So if we were all to switch to electric vehicles, the demand it would place on the electric grid is significantly larger than the current size of the electric grid. This is not something that we can just tomorrow, everyone buys an electric vehicle and starts plugging it in. We don't have the infrastructure or the production capacity to meet that kind of demand. There are a few things about the electric grid that are important to keep in mind as it pertains to switching from what we're currently using, which is largely based on fossil fuels, to what is often advocated for. And I don't have any issues with renewable energy, but it's important that we recognize where that energy works and where it doesn't work. What are the upsides and downsides of using any form of energy, and not have it simply as a given that this is what's going to work in any situation. If we take a look at the energy grid, there are three things that are important to keep in mind, especially with a lot of discussion about transforming the energy grid off of fossil fuels and onto renewables. First of all, the energy grid is not a battery. There is no storage, virtually no storage for the power grid. There's a small amount of storage that typically goes into dealing with certain spikes in demand. But there's certainly nothing that is capable of having long-term storage of energy from the power grid. And when I say long-term, I mean more than hours, actually more than minutes even. So when you produce electricity, you have to consume that electricity within the light travel time between the production location and the home or the business where it's being used. You have to use it right then. And so the production has to meet the demand at all times within a tiny fraction of a second. There's an example from the UK where there's a very popular, I think it's a soap opera called The EastEnders, and it happens in the afternoon right around tea time. And when EastEnders goes for a commercial break, everyone in the UK that watches it, which is basically everyone or some large fraction of the population, would go and they would turn on their electric tea kettles, and it would cause a large demand, like instantaneously a large demand on the electric grid. And it was so bad that they started making contracts with other nations like France and the Netherlands to supply the electricity just at that moment when people would turn on their electric kettles. A similar thing happens in the Super Bowl. There's roughly a 10% drop in water pressure in certain localities when the Super Bowl halftime starts, because you have to meet the water demand. You have to supply the water demand when it's needed. You don't get to choose necessarily when that happens. So that's one thing to keep in mind. It's very, very difficult to store electricity. And right now, there's nothing that we have that scales up to even a small fraction of the total energy that's in the grid at any given time. Another thing that's important to remember is that power plants can't turn on instantaneously. You can't just go to a coal-fired power plant and say, we need the electricity now, and expect it to function. It takes about 8 hours to bring a coal plant up online and have it operating at its best, at its kind of peak conditions. Nuclear, if you start nuclear from scratch, it takes about the same amount of time. But if you have nuclear energy running and then you turn it off, you have to wait 3 days before you can turn it back on, because there are certain things that are produced in the nuclear reactor that slow the reactor down. It make it so that it can't function until some of the byproducts decay away, and they have a half-life of order a day. So xenon in particular is a poison that prevents you from turning a nuclear power plant on immediately after you've turned it off. Unless Comrade needs something done right now or else, which can perpetrate all sorts of disasters. If you turn a nuclear power plant off, you have to turn it back on. You have to wait for 3 days before you can turn it back on. With natural gas, which in Nevada is the most common form of energy, this one, you can turn it on in minutes or hours, depending upon the design of the natural gas turbine. So the third thing to keep in mind is there are basically two different ways of using a natural gas turbine. There's the inefficient way of using a natural gas turbine, and this one you can turn on in minutes. It's basically, natural gas turbine is essentially a jet engine. You have a jet engine sitting out in the parking lot or in the facility. I should point out this natural gas power plant right here. This is the one that's located I think it's in Henderson. It may be across the border, but this is I-515 running around this way. And so this is the power plant you can see from the side of the road by kind of between Tropicana and I think this is Russell Road down here. So that's a fairly large natural gas power plant in the Las Vegas Valley. So there are two basic types of natural gas generators. One of them is a jet engine. You just put the natural gas in it, you burn it, and then the turbine runs, and that's where you get your energy from. However, the exhaust that comes out of this kind of natural gas power plant is still at high temperature. And you can still use that high temperature to boil water if you can connect it to a steam turbine. So if you start with a generic natural gas turbine, and you take the exhaust and funnel it into a steam, like a boiler, then you can get a much more efficient natural gas electricity generation. However, because it operates with a boiler, you have to heat up the water and you have to get the steam cycle going, and that takes hours. So at that point, if you want to run natural gas efficiently, you have to give it several hours of lead time in order to get the steam cycle running. All right, let's take a look at what were to happen if we were to immediately switch over, or not even immediately, if we were to switch over simply to solar energy. In the southwestern United States, there's abundant solar energy, which isn't true in other places where I've lived, like in Seattle. But this is one place where we do get a lot of sunshine, and so I'm all for capturing all of the energy that we can from the sun. Have no problems with that at all, especially if we are otherwise using the surfaces for nothing important. This is the Prim Valley, where we have the Ivanpah, so the solar collector arrays. There are two different types of solar energy generation that you get. One of them is through a collector, where you have mirrors that reflect the sunlight up to some kind of hot cell, where you'll either boil water or you'll heat up some substance, and then you boil water with that substance. And the other one, which is increasingly more common, is photovoltaic, so having solar panels. So this is a solar panel array here, and then these are the solar collectors. There's plus sides and upsides and downsides to both of these technologies, but one thing that's important to note is that right now we don't know what the future looks like in terms of how you deal with the maintenance of these arrays. So solar energy right now is a fairly small fraction of the total energy that we use in the United States, something like less than 1%. If we were to switch all of our energy demands over to solar energy through some form of magic, it would require replacing 500,000 square meters of solar paneling every day forever. If you want to have solar energy be your baseline, and this is being very generous, it's probably a factor of 2 larger than this. If I'm being very generous with what you can do with solar panels, it requires replacing at least 500,000 square meters of solar paneling every day indefinitely into the future, as long as you want to have electricity. So what do you do with the solar panels that you can't recycle? We don't know the answer to that question. Right now, the answer is you ship it over to a third world country and let them deal with our waste. So there are some downsides to this that are important to note, but it's more complicated than just what you do with the waste in the long term. So this is a famous plot for those who are in the business called the duck graph. So the duck graph is the difference between the electricity demand of a given location. So in this case, it's California. So what's the demand for electricity compared to what is supplied by something other than solar? So this is the demand minus the contribution from solar. So solar energy, the sun is only up in the middle of the day. And so the demand for other sources of power production goes down in the middle of the day as the amount of solar energy increases. So as you contribute more solar energy, the demand on the baseline, like the coal power plants and stuff like that, drops down because you're supplying it with solar energy. And then when the sun sets, which is in the kind of early evening, the sun goes down, and then you have to meet that demand with something else, something besides solar. So there are 3, if we take a look at those 3 things to keep in mind from before, this is what that translates to when it comes to how do you supply the energy needs of Californians throughout the day. You can't store electricity on the electric grid. And so as you increase the production of solar energy, you actually decrease the amount that you can supply with a baseline operations. So a coal power plant or a nuclear power plant, you have to eliminate coal and nuclear power plants from the electric grid as you increase solar, because you have to use the energy as it's produced, and you can't store excess energy on the grid. So the baseline production has to go down if you do that. The next thing that happens is, because the baseline production is so far down, then you have to ramp up. When the sun starts to set, you have to ramp up with some other form of electricity production in order to meet the demand as the sun is going down, but demand actually continues to rise. The demand for energy doesn't peak until about 7 o'clock in the evening. And so you have to be able to have on the electric, like connected to the grid, other forms of energy besides solar equal to the peak demand, and that is up here. And the only thing that can ramp up by this amount, I should point out over here that the scale breaks. I didn't produce this plot. The scale breaks down here. There's a big jump between 0 and 10,000, and then it's linear after that point. So it's about a factor of 2 that you need in the supply, ramped up over a couple of hours in order to meet the demand here at the end. So the only form of energy that we have that can ramp up this quickly to meet this demand is natural gas. And so if you want to convert over to solar energy right now, solar energy requires the low efficiency version of natural gas to supply the peak demand. So all of this production is going to be through the low efficiency version of the natural gas production, because you don't have the 8 hours that you need to get the steam boiler working up to its optimum level. You can only ramp things up on the order of minutes, which means that you're only dealing with Jeremy, the jet plane, and not Jeremy and Thomas working in tandem. Okay, so this is why we rely on fossil fuels, because fossil fuels, they don't have this intermittency, and so that's what we use. If we look again back at this thing, so this is again the energy use in the United States. Fossil fuels, natural gas is a huge component of electricity generation because it's become a lot cheaper, especially over the last decade. If you look at the same plot from the 1980s, which you can do because it's all online, you'll notice that in the 1980s, this was almost all coal. But as natural gas got less and less expensive because of new mining technologies, like through fracking and stuff like that, natural gas has become a more significant contributor to the electricity production, but it's still used in homes for water heaters and stuff like that. But natural gas, coal, and petroleum, those are the main sources of energy that we use because of the way, because of the fact that we can carry them with us, and some other things that I'll talk about in a minute. The reason we use natural gas is because of how energy dense they are. So there's a large amount of energy that goes into replacing the chemical bonds from hydrocarbons with bonds to oxygen. Oxygen bonds are a bit stronger, and so if you can separate the hydrogen and the carbon from each other and replace that with oxygen, then that releases a bunch of energy. And that's the energy, I mean, that's where the flame comes from. That's where the heat comes from, that you use to boil the water to make the electricity, or that you use to expand the gas in the piston of a car engine. So it's breaking these hydrocarbon bonds, replacing them with oxygen so that you get water and carbon dioxide coming out. You'll notice, so this is propane here and methane here. The ratio of carbon dioxide to water that you get is worse, since carbon dioxide is the thing that we want to cut out of the economy, or at least of the electricity production as much as possible. It gets worse the longer the hydrocarbon chain. So the longer the hydrocarbon chain, the more carbon-carbon bonds there are and the fewer carbon-hydrogen bonds there are. And what you want is as many hydrogen atoms as possible in your fuel if you want to reduce greenhouse gas emissions. So if you start with propane, you'll get 3 carbon dioxide for 4 water. But if you start with methane, you get 2 to 1 water to carbon dioxide. And so it's significantly better in terms of the carbon footprint when you burn short hydrocarbon chains. This is why the United States has actually reduced its carbon footprint, among other reasons, but this is one of the reasons why the United States has reduced its carbon footprint, is because natural gas has become a lot more common source of energy than coal, which has long hydrocarbon chains. And so we get the same amount of energy, but with a significantly smaller amount of carbon that's produced. For carbon dioxide, or for hydrocarbons, you get roughly 50 megajoules per kilogram. So the units here aren't that important, but the number is important. 50 megajoules per kilogram. The megajoules per kilogram, you know, that's like some unit that doesn't make, it's not particularly interesting, but the 50, keep that in mind. So 50 units is what you get from 50 units of energy per kilogram. If you were to go to nuclear power, the amount of nuclear energy that's contained in a similar similar number of atoms is significantly larger. The nuclear forces are a fundamentally different force, and they have fundamentally different bond strength associated with them. If you have uranium, for example, or thorium, any nuclear fuel is about the same, you're looking at 80 million megajoules per kilogram. So 80 million units of energy per kilogram compared to 50 units of energy per kilogram. So just to give you an idea of how different these numbers are. These numbers are so amazingly different that it's hard to even comprehend them. But here's a couple of ways of illustrating that. If this is the amount of energy that you get from hydrocarbons per kilogram, so you can get a value menu for about, we'll say $10 because it's a number that I can multiply fairly easily. If you were to change that from, so this is what you get from chemical energy. If you were to change that to nuclear energy, for the same mass in nuclear energy, you could buy this house, drive this car, send your children to this university, that's Harvard, in case you can't tell, send your kids to this university, and then have this chef make you this value meal, and still have money left over. That's the difference between the amount of energy that you have per kilogram in chemistry versus what you have per kilogram in nuclear. It's a huge difference. Another way to think about it is my energy consumption over my lifetime, and pretty much any American is essentially the same, is about 1,000 train cars worth of coal. So I will use the equivalent of 1,000 train cars worth of coal in my lifetime, assuming I live 100 years. So there you go. If, on the other hand, I were to look at how does this compare to what I would need for nuclear energy, the answer is about one baseball-sized, a baseball-sized piece of nuclear fuel is all of my energy needs for my lifetime. And that's all of my needs, not just electricity needs. So there's a huge difference in the energy density that you have between uranium, or between a nuclear fuel and chemistry, because it's a different force, and the different force has a significantly different bond strength. And so when you release that energy, it doesn't take as much substance to produce the same amount of energy. Now, a real quick comment about nuclear energy. This was asked by all the people that I practiced with, and so I'll bring it up now, is that nuclear energy is, of the major providers of energy in the world, nuclear energy is the safest by far. This shows basically the death rates from energy production per terawatt hour. This comes from Our World in Data. If you ever want to see what progress looks like, this is a place to look. Our World in Data, it has these kinds of graphs, and you can look them up for all sorts of things like literacy and infant mortality and energy production and food production and stuff like that. So this is the death rates per terawatt hour for each of these different sources of energy. What's not included here is what about 1 billion people use in the world, which is animal dung, which is worse than all of these things. Indoor air pollution is one of the major killers of people in the world. So if you compare coal to nuclear energy, it's about 300 times more deadly than nuclear energy, and natural gas, which is the safest of the primary sources of energy, it's about 30 times more dangerous than nuclear energy. Another common misconception that people have about nuclear energy is that they assume that it's the chemistry that's important, and it's not the chemistry. And what I mean by they assume that the chemistry is important is that you hear people, if you hear uranium, to the typical person, uranium is uranium is uranium. It's all the same. But that's not true when it comes to nuclear physics. So this shows the kinds of nuclear fuels that we have. The possible nuclear fuels are the ones that are in red. So that's uranium-233, uranium-235, and plutonium-239. Also plutonium-241 and americium-241, but those are less common, and so, well, we don't use them, but they could be used in principle. So these are the common nuclear fuels. Things that you can produce those nuclear fuels from. So for example, plutonium isn't something that's found naturally in nature, but uranium-238 is. And so you can breed uranium-238 by adding neutrons to it and have it convert into plutonium-239 and then run your nuclear reactor off of plutonium-239. So the difference between a good nuclear fuel, which is, for example, uranium-235, and something that is not a nuclear fuel by itself, which is uranium-238, is 3 neutrons. Okay, that doesn't seem like much because it's still uranium, and so when people think about uranium, it's not obvious what the difference is. But the difference in chemistry, the difference is almost non-existent. Chemically, these are essentially identical, uranium-235 and uranium-238. But physically, they are very different when it comes to how do they absorb neutrons and how do they interact once the neutron is absorbed. So the difference between 3 neutrons is the equivalent of the difference between lead and gold on the periodic table. So the difference in chemistry between lead and gold is the same difference in nuclear physics between uranium-235 and uranium-238. These are not the same animal. So anyway, something to keep in mind. So if you want to have a nuclear reactor that functions, you need to be able to take your nuclear fuel, so in this case it's uranium-235, and you need to be able to split it into some low mass daughter particles so that you can capture some of that energy that's bound up in the nucleus. That will produce a bunch of neutrons that you can then feed into this cycle. So you have to absorb a neutron to begin with, it breaks apart and emits more neutrons. So you need to have enough neutrons to sustain the reaction, and you need to be able to catch the neutrons. It's difficult for these nuclei to catch things that are moving too fast. So the neutrons that come out of this interaction are moving at very high speeds, and you need to slow them down in order for them to be caught by the next generation of reaction. So to allow the reaction to propagate, you need to both produce these neutrons, slow them down, and then capture them onto the next nucleus, which then breaks apart and then produces more neutrons, which you then have to slow down. And that is basically, that cycle right there is why nuclear reactors are designed the way that they are. So they're designed with specific things in mind. You have control rods that can shut down they can absorb the neutrons and shut down the reaction. So they absorb the source of neutrons that allows the reaction to take place. You have a moderator that slows those neutrons down so that they can be absorbed by the nuclear fuel, which is here is in gray. And then you have a coolant, and the coolant, I'll put coolant in quotation marks. The coolant is there to cool the reactor, but that's actually the thing that drives the turbine. So you take the coolant and you bring it over here and you boil water with the coolant, and then that boiled water is what goes through the steam turbine. Some nuclear reactors actually have the coolant, boil the coolant directly. That's a boiling water reactor. In the United States, most of the reactors are pressurized water reactors where the coolant is separate from the water that is boiled to produce the electricity. But say the Fukushima reactors were actually boiling water reactors where it didn't have this separate loop out here. So anyways, the important things in the design are it has these control rods that absorb things so that you can shut the reactor down. They have a moderator that slows the neutrons down so that they can be absorbed. And they have the coolant, which prevents the reactor core from melting through the cladding, and also is what is used to drive the electricity production. But there are, most of the time, in most reactors that are used today, the moderator and the coolant are the same substance. So you use water to moderate the neutrons because you have hydrogen atoms in the water that can slow things down. And you use that same water to drive the other cycles in there to cool the reactor. So in most reactors, but this need not be the case. So it certainly wasn't the case at Chernobyl, where the moderator was one thing and the coolant was another. But for most reactors that are used today, the moderator and the coolant are the same substance, but that in principle, they're separate substances. So there's an issue that you have when you're working with water, and that is that you don't have enough wiggle room with water because water melts at 0 and then boils at 100. And so you only have 100 degrees of temperature to work with unless you go to high pressures. So if you go to high pressures, then you have more, so then the boiling point goes up, like a pressure cooker, the boiling point of the water goes up when you pressurize it. And so if you're going to make a reactor and you want to have water in your reactor core, you have to pressurize the reactor core or do something with it, because otherwise you're going to evaporate all the water and then you can't cool the reactor core. So the downside of working with water is it has a very narrow range where the water is liquid. Unless you go to high pressure. And when you go to high pressure, that's where you have to bring in a whole bunch of engineering to keep this pressure cooker contained. There are other substances where you can have a much wider range in temperature where it can be liquid for a lot longer. And I'll be talking about that momentarily. But with water, you have this issue where it only stays liquid in a relatively small range of temperatures. Okay, another issue that you have when you're working with water is that the water will separate into oxygen and hydrogen, and then what will happen is the oxygen gets absorbed onto other things, and then you react with the atmosphere and it creates explosions. So all of the explosions that have taken place, all the nuclear reactor explosions, that all 3 of them that have taken place in the last 50 years or longer, have been steam explosions and not nuclear explosions. These are not nuclear bombs that are going off. The reactors are incapable of actually exploding the same way that a nuclear bomb explodes. It's physically impossible for them to do that because you can't sustain that kind of reaction by design in the nuclear fuel. What has happened instead is that all of these things produce a lot of steam. The steam is at high temperature, and then you get a steam explosion where the hydrogen that gets stripped off of the water molecules recombines with oxygen from the atmosphere, and then you get a big explosion. So they're all chemical explosions that have taken place in these things, in the reactors that we've seen so far. With the reactors where we've had problems, which is Chernobyl, 3 Mile Island, and Fukushima, all of these reactors were designed in the 1960s. And so they're called Generation 2 reactors. So Generation 1 reactors were built after, like, kind of in the 1950s, and then they said, okay, here's what's working, here's what's not working, we'll make another generation. And the second generation of nuclear reactors were designed in the 1960s and implemented and built in the 1970s and early 1980s. All of the ones that we've had problems with are the second generation of nuclear reactors. And one of the challenges that they face is that you have to have an active system to moderate the safety. So if you look again at the reactor, you have to have an active system that keeps everything safe if the reactor core, like if the reactor gets out of hand or you need to deal with something. So the power has to stay online. And so you have generators and things like that that you turn on in order to keep the reactor core functioning and in a safe condition as you do whatever repairs need to be done. So that's one of the hallmarks of Generation 2 nuclear reactors, is that even though they are still the safest form of electricity that you can produce, that is the main failure mode, is that you have to have active cooling or active safety measures. The Generation 3 nuclear reactors, which were designed in the 1980s and built in the 1990s and through today, Generation 3 nuclear reactors don't have those kinds of safety requirements. They are designed specifically so that if there is a problem, you can walk away from the reactor and come back months later and the reactor is already in a safe spot. Like nothing will have happened. Anything dangerous will have been dealt with through gravity pulling the something melts down and then it flows because it's molten into some kind of storage container that is safe. And so the Generation 3 reactors, which are the ones that are being built today, these are reactors where you can leave them alone, turn off all contact with the outside world, and they will put themselves in a safe state without any interference. You don't need to have generators turn on to have them remain safe. So Generation 3 nuclear reactors and 3+, not only do they have better fuel efficiency, they use the fuel more efficiently so that they don't have as much waste that is produced. They have better thermal efficiency because they operate over a broader temperature range, and they are passively safe, meaning that you can walk away and you don't have to worry about things leaking out into the environment. This is Generation 3. Right now, what is being developed is Generation 4 nuclear reactors. And these are also, in this case, they are fundamentally different in their design. Generation 3 nuclear reactors are kind of the last step in the chain of pressurized, like using water, kind of the existing nuclear reactor designs. This is the end of the line for those reactor designs, is the Generation 3. Generation 4 kind of radically redesigns what the nuclear reactor looks like, and brings along with it several major benefits. So not only are they more safe, so not only is Generation 3 more safe than the current already safest form of energy production, Generation 4 is even more safer than Generation 3 nuclear energy production. So they have even better safety features and even simpler safety protocols for how to turn a reactor off or how to let it turn itself off in the event of some kind of natural disaster. And in particular, the major hallmark of Generation 4 nuclear reactors is that they operate at significantly higher temperatures. So instead of operating at, say, 300 Celsius, which is what you get with those that use water, you have a relatively small range of temperatures where the water stays liquid of about 200 degrees. Your operating temperature is about 300 Celsius. You go kind of as high as you can. Oh, I forgot. I changed this. It's actually not, you don't go all the way to 300 Celsius. It's usually around 250 to 275 degrees, and I didn't change all the slides. So you're operating at a relatively low temperature, and so you get an efficiency that's about 35% so with the same amount of nuclear fuel, you have an efficiency that is about 35% with the current generation of nuclear reactors. If you were to switch to Generation 4 nuclear reactors, which operate either using, for example, molten salt, where you take salt, it's similar to table salt, but it's made out of other substances. It melts at about 500 degrees Celsius, and it stays melted clear up to 1500 or 1800 degrees Celsius. So you have a huge window where this stays in a molten state. It's not going to evaporate on you and then facilitate some kind of steam explosion or something like that, or cause a big increase in pressure. You can operate at low pressure because it's not going to boil until you get way, way, way beyond the operating capabilities of the reactor. And so these molten salt reactors operate at about 700 degrees, and that change from 300 degrees Celsius to 700 degrees Celsius takes you from 35% efficiency up to 50% efficiency. So this alone, operating at higher temperatures, means that with the same nuclear fuel, you get 1.5 times the amount of energy out. The same amount of nuclear fuel going in, 1.5 times the amount of energy coming out, because you're not wasting that energy because the process is more efficient. Another type of Generation 4 nuclear reactor, there are about 6 basic designs, and one of the most promising designs is called the gas-cooled high temperature reactor. This one, because you're cooling it with a gas instead of a liquid, you don't have to worry about it boiling. You only have to worry about it ionizing, and that takes place at temperatures like the surface of the sun. So these ones operate at a temperature that's even higher than 700 degrees, so about 1,000 degrees Celsius. And there the efficiency goes up to 65%. So that's a factor of 2 more efficient than the current generation of nuclear reactors. So the same amount of nuclear fuel, you'll get twice the amount of useful energy out of it with the high temperature gas reactors. So these are some of the differences between the old reactor designs and the next generation of reactor designs that are, they're being built, like the test versions of them are being built right now. Idaho National Lab is one place. Pacific Northwest National Lab is another place, Oak Ridge. These are the kinds of reactors that they're building in order mostly to test the properties of different substances, like the different materials that you would make the reactor from. Okay. Now, why this is important, why the Generation 4 nuclear reactors are fundamentally different as it comes to how do you deal with climate change. We're trying to cut back on the amount of carbon that we produce in the economy. And the main sources of carbon that we saw is not residential electricity production or even commercial electricity production. The main source of carbon that we saw comes from the transportation sector, and it comes from the industrial sector. Operating at 275 degrees Celsius or 300 degrees Celsius is not enough to get you to cut into the major contributors to climate change. These temperatures, on the other hand, 1,000 degrees or 700 degrees, there you actually can make inroads into that through nuclear process heat. So in this case, what you do is you take the nuclear fuel, you take your nuclear reactor, and when you're not generating electricity with it, you just take the heat, the high temperature material from the reactor, so it's at 1,000 degrees or 700 degrees, and you siphon that high temperature material off to some industrial site, and then they use that heat directly. So instead of using natural gas to produce the high temperatures that you need to make fertilizer, for example, so fertilizer production right here, you use natural gas burners to do that. So instead of using natural gas to get to those high temperatures, you just siphon it off of the nuclear reactor, and the high temperature is already there. So you can make fertilizer from the residual heat from a nuclear reactor. And that is 5%. That's half of the energy that's used by residential consumers is just going into fertilizer production. And so you can eliminate the equivalent of half of all of the electric grid for residential by transforming fertilizer production from natural gas as your source of heat to nuclear process heat, which has basically zero greenhouse gas emissions. Paper production, aluminum. So this is aluminum production, which most aluminum is made by like running electricity through it, but you can generate that electricity with nuclear instead of with fossil fuels. Some aspects of steel production you can transfer over to nuclear process heat, meaning that the temperature is in the right range to do that. So you can not only do existing processes with nuclear energy or nuclear heat, but you can also change fundamentally what processes, like how the economy functions. So you can either take existing products and make them with the energy that you get from nuclear reactors, or you can even have new products come online. So other places where you can use nuclear energy, this figure right here, this is looking down from Google Maps onto one of the largest water desalination facilities. So this is on the Arabian Peninsula near, I think this is near the UAE. There are millions of people that live there, and they get their drinking water from the ocean. And so you take ocean water and you have to remove the salt from it, and that takes energy. If you just take nuclear process heat, you can make a much more efficient way of removing the salt from the ocean water to provide drinking water for the millions of people that live in desert environments. So that's California could supply all their drinking water from ocean water if they had high enough temperature nuclear reactors to do this. Another thing you can do with these next generation of nuclear reactors is that they're designed to be small or to be put together a piece at a time, which means that you can provide electricity, nuclear electricity, to remote locations. Right now, some of the biggest carbon footprints per capita come from Arctic regions, so like Canada, Alaska, because the people make all of their electricity through diesel generators, because you don't want to build a gigantic power plant out in these remote locations because they can't use that much electricity. But if you have, with the Generation 4 nuclear reactors that are designed to start small and then to be able to piece them together to make a large kind of assembly of nuclear reactors, you can do that with these Generation 4 nuclear reactors. You can also take coal out of the ground, heat it up from nuclear energy, and melt it down and make jet fuel out of it. So some of the transportation sector that you cannot convert over to other forms of energy, you can take the coal from the United States, make higher quality jet fuel out of it because it has fewer particulates in it and it's more energy dense. So it's about 10% more energy dense than what you get from refining oil. And the big player in this is the last one, which is the hydrogen economy. So you can make hydrogen gas from nuclear process heat that you cannot make efficiently through other forms of energy. So, and if you have hydrogen gas, you can replace already, just with existing infrastructure, you can replace about 10% of the natural gas burners. 10% of the carbon footprint of natural gas burners you can replace by simply mixing together natural gas and hydrogen in the existing infrastructure. If you want to go to so you could have a stovetop You can imagine building a stovetop where you burn hydrogen gas rather than burning natural gas. You have to design it differently because the flame speed is a bit different, but you can build such a thing, and you can imagine converting all of the natural gas burners over to hydrogen gas burners by making that hydrogen gas through electrolysis or other forms of production using these nuclear reactors. So this is cutting into, rather than just worrying about the production of electricity, you're cutting into the major sources of greenhouse gas emissions through the industrial sector and the transportation sector. Now you're talking about the kinds of energy that you need if you want to have electric vehicles and drive them around, or have switch things over to the electric grid. Now you have a source of energy that's capable of meeting the demand, because there are thousands of years worth of nuclear fuel that's available on the Earth. It's produced in mine tailings all the time, but it's not extracted for political reasons that are an interesting discussion in its own right. So there's plenty of nuclear fuel available for many centuries of use by the human population, in particular in developing countries where there's an even larger population than what we have in the United States. So the moral of the story being that the next generation of nuclear reactors are safer than even the current ones, which are already safer than everything else. The fuel is much more abundant, and it's used more efficiently in the production of the electricity that we get. And not only is it used more efficiently, but there are more applications for it that can cut into the carbon footprint of these other sources or other uses of energy that we have in our society, to make cement, to make steel, to make fertilizer. These are the kinds of things that you can do with nuclear energy in the next generation of reactors that has not been available to us up until this point. So thank you for your time. I hope that you found this interesting, and I'm happy to answer any questions that you might have.
Thanks so much, Dr. Steffen, and we appreciate your time as well. If you have any questions, put them in the chat. I'll wait for a couple minutes, give you some time to type it out if you're looking at answering or asking anything to Dr. Steffen before we conclude. I'll give everyone a minute or two. That was really interesting. Thanks, Jason.
You're welcome.
So someone asked, do all these uses have to be located very close together?
So it depends on what you mean by very close together. So if you want to siphon off industrial, like nuclear heat, and port it over to an industrial facility, kind of the radius that you need is about 1 kilometer. So about half a mile is where you would station them. So you would have a power plant located in some location, and then within a mile, you could imagine having it go for a mile, but a half a mile is more kind of the optimum distance. So you could have a nuclear plant with a bunch of other plants located around it. Let me switch to a different view so you can see my hands. So you have that, and you have a bunch of different plants located around it where they can siphon the heat off, kind of feed off of it in that way. So it gives you a fairly large footprint where you can station these things. And you would put a power plant in an industrial part of town anyways. So the answer to that question is mostly yes.
Okay. So someone.
Yeah. Let's see. Go ahead.
I was just going to say, it's not really a question, but someone said, going back to gas turbines, you mentioned that they have an 8-hour startup time if they are connected to a boiler. This seems like a solvable engineering problem, keeping the boiler hot at all times. Do you want to elaborate on that at all?
But if you're keeping the boiler hot at all times, then it already loses the efficiency because you have to keep it hot somehow. And so you have to keep it hot by burning some other source of fuel to keep the temperatures high. And so the cycle it lags too much behind. The 24-hour cycle is too small compared to the 8 hours, the several hour temperature cycle in the boiler. So if you keep it hot all the time, I'm sure that gets used already because that's a major source of savings. But I don't think it's, for the most part, when you're keeping it warm, you're keeping it warm with some form of fossil fuel that's not being used for other applications.
And then looks like one last question. Any estimates on when the first Gen 4 reactors may go into production use?
So it's almost on a weekly basis where there's some new small, I mean, all the breakthroughs are kind of small, where there's some new breakthrough in Generation 4 reactors. It really is boiling down right now to what materials do you make things out of? So what pipes do you build something where you're going to have 1,000 Celsius or 1,000 Kelvin fluid going through it? Because you can't just make it out of, tinfoil or toilet paper rolls or something like that. You have to have some alloys that can withstand 30 years of prep. So most Generation 4 reactors are supposed to be licensed for 80 years with some kind of maintenance in there. So you have to be able to have something that can last for a decade under these conditions. My estimate is that we'll probably get commercial Generation 4 reactors built within the decade, and then ramping it up to scale will probably take several decades. So if you could dictate immediately what would happen, you would go with the technology that currently works, which is Generation 3, as you continue to invest in making Generation 4 reactors viable to bringing them onto the market.
Okay. One more, let's see, a couple more questions came in. Let's see, is the TerraPower approach more efficient than microreactors?
So I'm not sure what the TerraPower approach is, but it makes me sound like you have big, gigantic nuclear reactors. And the answer to that question is, so I'm going to assume that that's what you're speaking of. The answer to that question is it kind of depends on what you want to do. So the challenge that you face with big nuclear reactors, so if you look at in Arizona, so Palo Verde is the largest nuclear reactor in the United States. And those are like almost 2 gigawatt reactors. They're 1.5 gigawatt reactors. So those are big nuclear reactors each. When you build something that big, your initial cost is large. And so that's why when people say nuclear energy is really expensive, it is expensive because you're building kind of the biggest things that you can. Where with the small modular reactors, you can build them a little bit at a time and kind of piece it together. So you don't get, the payback is over a longer period of time when you go to the small modular reactor design compared to a single big reactor. But I think it really boils down to, if you have a small variety, you don't want to have a large variety, which is what we currently have, which is why it's so expensive. If you have a small variety of options to choose from, then you can pick which reactor best works in this situation. And so an advantage that you get with small modular reactors also is that you can make the grid more resilient, because you can even place them, you can have them integrated more directly into the grid rather than having it way out in the middle of nowhere and piping the electricity in. And so you get less losses in the transmission and stuff like that. So there's a variety of things that you can consider that are available to you with a smaller reactor design. But I don't really have a preference one way or the other. Ultimately, the fuel is the most energy dense fuel that we have available to us.
So it looks like 2 more questions. So the second to last is, what do you see as the challenges for Gen 4 coupled with SMRs and smart grids meshing into the existing grid infrastructure?
I don't see that there's really that much of a challenge for them, provided that you can. So if you try to couple it directly with the development of solar energy, then you run into the problem that solar energy, like nuclear power plants, you can't just shut them off and turn them back on again. You could imagine heating up a reservoir of salt, some kind of molten salt, both with the solar and with the nuclear energy. So they combine to heating up your substance, and then you're using that molten salt, not as your nuclear fuel, but as your working substance that you're driving your steam turbine with. So I suspect it's not that they're incompatible, but you have to think twice about it before you introduce them. But just introducing them into the grid, I don't think there would be that big of an issue.
Let's see. When will fusion reactors? Oh, I'm gonna not be able to say this, but you can probably see it in the chat, Jason.
Tritium.
Be able to replace fission.
So my understanding is that ITER in France recently got a plus sign on their net energy, like their energy production from a fission reaction. I think I would not place any hope on that coming online in my lifetime, simply because, you know, it's easy to say we have this technology that's going to revolutionize everything. Now you don't have to worry about the future. I think that any technology that's going to take over major portions of the electric grid is going to have the same kind of ramp up time that everything else has had. We've had 150 years of coal power generation to make it as safe as it is now, which compared to what it was in the past is significantly safer. So it takes many decades to develop the technology and the know-how and the, you know, to make all the mistakes. So people who say that, you know, we can switch to renewables and it's immediately, you know, all the problems have been solved, that's just not right. And I'm not saying we shouldn't switch to renewables. What I'm saying is that renewables are going to have the same learning curve that coal has had and that nuclear has had. Nuclear is a pretty well established technology that's been around since the 1940s. So we're coming up on 80 years of nuclear energy. So that's a pretty long baseline to make the improvements that you need. And switching to any other technology, including nuclear fusion, is going to have a similar lifetime of the first fusion reactors aren't going to work very well, so they're going to have to make another generation, and it takes a decade to figure out like what you've done, and then to you know, make the improvements. And so, you know, it's about a century for something to make it into prime time. So I'm guessing that the first commercial fission power plant would probably come online about 80 to 100 years from now, is my guess.
Okay. And one last question came in, and then we'll wrap it up just because it's a little bit past the hour. So when we hear that countries like Germany have decided not to pursue nuclear energy, do those restrictions apply to the new Gen 4 type reactors?
I suspect the answer is yes. A lot of Generation 4 research is being done in Denmark, being done in the UK, it's being done in Canada. There's quite a bit that's being done in the United States, but the United States has different regulation infrastructure that makes it a bit challenging. So that in Canada, they're a bit more flexible in terms of, you know, we're going to design a regulation around this one technological thing, and then they'll advance the technology up to that point, and then they'll kind of adjust the regulations as they go. Where in the United States right now, it's not that fluid. You kind of have to satisfy the regulations that apply to technologies that aren't included in it's kind of messy because of why solve a problem if you can run your campaigns on it indefinitely into the future. And so in Germany, I don't know exactly how they're going to deal with this because their electricity prices are basically twice what it is in France, and France gets most of their electricity from nuclear. And especially in the developing world. So China is investing a lot in Generation 4 nuclear reactors, as is India. And they have a larger population. So ultimately, it may not matter what Germany does because, well, for one thing, they're a rich enough country that they can spend more money on electricity. But if you were to go to India and say, now we're going to raise your electricity rates by a factor of 2 because we don't want to use a technology that sounds scary, you know, you're talking about affecting the bottom end of the socioeconomic ladder, are the ones that are affected the most by poor decisions when it comes to the energy sector, because a larger fraction of their income goes towards keeping their homes heated or the air conditioner turned on. More people die from cold than die from heat every year. So more people die from lack of energy than they do from the existence of energy.
Well, thank you so much, Dr. Steffen. We really appreciate it. If anyone has additional questions, you can email them to me. I put my email in the chat, and I will pass them on to Dr. Steffen, and he will get to answering them. Again, just a reminder that we will have another presentation in September on Wednesday, September 30th. It's with Dr. Audi Picard. And thank you so much again for joining us. We appreciate you taking the time out of your day. And thanks again to Dr. Steffen for your presentation.
All right, thanks, Corey.
Thank you.